Hey everybody, we are looking at critical points and points of inflection. So we're going to have this graph we're going to discuss in a moment, but first let's talk about some vocabulary. And this one is a really important piece. Critical point. Sounds important just from the name, doesn't it? So x equals c is a critical point if and only if f equals c is defined and f prime of c either is 0 or is undefined. This is the only thing that makes a critical point a critical point. And remember that if and only if phrase just means that, like your if then statement, you can reverse that. So for a critical point, you might see a local max or a global max, local min, global min. I'll talk about those in just a second too. Or you might see a plateau point, which I will also talk about. Sometimes you'll see the phrases relative and absolute versus local and global. Okay, so local versus global mins and maxes basically means, like, if you're looking at a function, the local max is just it's the highest thing in its immediate neighborhood. It might not be the highest point for the entire function, but it's just the highest point for, like, if you were standing there and you walked either direction, you would have to walk downhill. Or a local minimum, if you were standing there, you would have to walk uphill. So versus a global is the global min or max would be the highest or lowest point over the entire function. If we were talking about the surface of the Earth as a function, like the global maximum would be the summit of Denali. But say a local maximum would be the top of any hill. So it's just the highest spot in its neighborhood. It doesn't have to be a big peak. It just has to be higher than what's around it. If you were standing there, you'd have to walk downhill. So don't overthink those two very much. So looking at this function, there's a lot going on. Another thing that's in there is something called a point of inflection. So let's look at that definition. So x equals c is a point of inflection if and only if f double prime of x changes signs at x equals c. So, and we'll get into an example of this in the next video. So you'll see the function switch between being concave down, like a frowny, or concave up, a smiley. So concave up, you have a positive second derivative. Concave down, you have a negative second derivative. And the point of inflection is the point where you're switching between those. So like on a sinusoid, every point along the sinusoidal axis is a point of inflection. And then finally, our last bit of vocabulary, and then we'll go back to the graph and inspect it all, is a plateau point. And a plateau point happens if x equals c is a plateau point if and only if f prime of c equals 0, so it's flat ground if you're walking along it, but f prime of c doesn't change signs at x equals c. So for example, if you go hiking, you've probably experienced this. You're walking uphill for a long time and then you hit a flat spot, you're like, woohoo! And then it turns right uphill again and you're like, dang it, that's a plateau point. That uphill, flat, uphill. Or you can be walking downhill, flat, downhill. So let's look at all these pieces on this really kind of heinous graph. So one thing we have to watch out for is an endpoint. Endpoints are going to always be critical points because the definition of a critical point is f of c is defined and f prime of c either is 0 or is undefined. So since a derivative is a limit and a limit has to exist from both sides, an endpoint is a critical point. And in this case, our endpoint happens to be a local maximum. And yes, it is a critical point. Okay, at x equals 1, it's clearly a minimum. And it would be a local minimum. By the way, a global minimum is also a local minimum because it is the lowest, but you can also get more specific and say, actually, that's the lowest for everything. Unfortunately, I did not make this graph very clearly. I created a local minimum that's really clearly, let's say it's that, but whatever. So here's a local minimum. And notice also that it's pointy right here. So we have a cusp or a corner. So we have a local minimum, we have a cusp. And if you look closely at this, notice how on the left side it's concave up, on the right side it's concave down. So this guy is also a point of inflection. Goodness me, that's a busy point. We have a maximum clearly here, and that's not quite our global maximum, it's just a local maximum because it's not the highest for the whole thing. Our global maximum happens here at x equals 5. And then as we go, and so looking at this function, as I head from 1 towards 3, I go from concave down to concave up. That's very clear. Somewhere in between it has to switch between that. And if we look closely, it's right here. So at x equals 2, we have a point of inflection. I'm going to write just POI for the sake of space. So point of inflection. Our textbook writes PI, but that just seems like a Greek letter P to me, so I try to avoid that. But we do switch from concave down to concave up. When I put that point in, it actually makes that show a little bit better. Okay, continuing across at x equals 3, we have a local minimum again. We have a corner or cusp. It doesn't really matter much if you call it a corner or a cusp, but you can see that it's kind of an abrupt switch there. So it is a corner. I'll call it a corner. There are some technical differences, like this being like a pointier thing. It's more of a cusp, but than a corner. It doesn't really matter a whole lot between cusp and corner. And since we switch from concave up to concave down, we have a point of inflection here. And my cat is yowling outside the door. Okay, as we continue along, at x equals 4, see how it goes? We're going from uphill to flat, back to uphill again. That's that plateau point I was talking about. That when you're hiking and you're like, yay, it's flat, and then you go, oh, never mind. Notice that on this plateau point, we went concave down to concave up. That plateau point is a point of inflection. Moving along towards 5, we have a global max, we have a cusp, and looking at this, is it a point of inflection too? Well, no, because it's concave up on the left, concave up on the right. So it's not a point of inflection. A corner or cusp can be a point of inflection, but usually actually it's not. And this cusp is a critical point because the derivative is undefined. And we know it's a maximum because our slope actually switches from positive slope to negative slope as you look to each side, and it's the highest spot nearby. Okay, finally continuing on to 6, we have a minimum here. It's not a point of inflection, it is just a minimum. X equals 7, it looks like we have another point of inflection because the concave up to concave down switch. And then on our endpoint, this is a little weird. Notice that this is, even though there is, like our function ends here, but with an open circle, it's not a minimum, it's not considered a maximum, because in order to name a maximum, you would have to say what the y value is. And since you're like approaching the y value, but not actually getting there, it doesn't actually count as a maximum. And that's a little bit trippy and weird to think about. But it's like, well, what's the x value? 7.9? How about 7.99? What about 7.999? And you can go on with that argument forever. So because of that open circle, it's not a maximum. But we still consider it an endpoint because, yeah, we're going to end here. So there's our intro to our vocabulary. Stay tuned to see this stuff in action a little bit more.